Hello everyone. See transcripts. Yeah, if I have any more technical difficulties like last time where I wasn't sharing the screen, just shoot a message in the chat. Yeah, I'll give it a read, but hopefully everyone can see me. All right, cool. So we will continue on today with what we learned last workshop. Last workshop, remember, was to do with rectilinear motion. That's movement in a straight line, pretty much. And yeah, I guess the main point of today is it's still on kinematics, but we're going to branch out into 2 dimensions, which you will see is going to have, like, it can be seen in a lot of different forms, right? And yeah, I really like the lecture today. So if you sat in that, you'll see that the way that Jing organized the information was really good. So I've kind of just summarized it down here. Basically, you can break it up into coordinate systems. So yeah, you want like a 2D grid of some sort. That's for these first 2 ones. So for the XY plane, that's the case, and for the normal and tangential plane, that's also the case. Polar is a little bit different, and we'll talk about that shortly. But I'll just go through these one by one, and yeah, I'll give you examples. So let's zoom in. So the first one that you've learned and that you've been applying even since the first workshop is using an XY plane. So motion on a flat ground, for example, right? If you remember from the first workshop, we had a question which looked kind of like this, where you had a box and it was pulling against the ground, and in that first workshop, it was to do with static friction, but you might see some questions which you'll have to utilize kinetic friction because the box will be in motion, right? That's an example of motion on a flat ground. Just give me a second, I will pull up my notes quickly. And if anyone wants to look at the notes as we go, I've been starting to upload my draft of the notes into the folder. And so if I scroll too quickly or whatever, you can look on my Google Drive and you'll see the draft of the notes. What I usually do is, after I've completed this workshop, I go back, I clean up a few things, and then re-upload them formally on Moodle. Yeah. All right. Yep. Okay. So yeah, and just reiterating how this kind of works in this scenario. Basically, in the up and down direction, so I guess the Y direction. In the Y direction, the sum of the forces will be equal to 0 because this rope that's tugging the box, it's not like yanking the box so it flies off the ground. In that case, we're in static equilibrium in the Y direction. But for the X direction, if the box is able to overcome the static friction, it's now being pulled by the rope. And yeah, in the X direction, we have F is ma, right? It's kind of how it would work in that situation. For projectile motion, if you remember this from physics, physics 1A or high school physics, it might look something like this, where you have someone who throws a ball or a cannon which is being launched, which is launching cannonball, and projectile motion perfectly uses the XY plane because of three assumptions that we make. The first one is that mg, the gravitational acceleration is pointing perfectly downwards. So it'd be I'll do it like this. It would be 9.81 meters per second squared of acceleration acting downwards, in the negative y direction, right? And the other assumption that we make is that in the x direction, we don't have any acceleration or deceleration, right? That's kind of our model that we use for projectile motion. And I guess just adding on to the AX is equal to 0, that's because we have to assume that there's no air resistance, and so there's no deceleration due to the wind or whatever, right? So that's projectile motion. With relative motion, I'm going to move this slightly. I'm going to quickly check online to see if there's problems, because there's problems at the start last time. Seems we're good. Okay. Okay. So relative motion. Usually we use the I and J unit vectors that we were talking about earlier in the course for relative motion. So I'll give you an example. If we have like a plane or something, we're looking at this from top down or like plan view, right? We have two planes like this, right? We can break up their velocity into the horizontal, into the XY planes, right? Pretty much. If we're looking at this top down, right? And we will be utilizing, Oh, sorry. That's all right. Yeah, they're unit vectors like that, and you'll see how that there's like a little formula for that as well, but it helps to break it into those components for those questions. So next we have our normal and tangential planes, and as far as I could think of, there's two situations where you want to use the NT planes instead of XY, right? The first one is motion on inclined ground. Incline might be like a hill or something. So when you're taking the sum of the forces, you can take it in the n and t directions. And the reason why you might find this useful, by the way, for its weight, like that. So its normal force would be like that. So the reason you might find this useful is because if you take the sum in the y and or the x direction, in these questions, you might end up with too many unknowns. And so when we break it up into the n and the t directions, you can find that unknown acceleration going in the tangential direction, as well as the normal force independently, right? But that's still grounded, right? Similar to motion on a flat ground. And nextly, curvilinear motion, which we will talk about a bit more later. So say I have a car going around like a race course or something that's circular. You'll find that there's your normal component for your acceleration as well as your tangential, right? And the way that you work these out will be different. The normal component has a formula, which is b squared on r, whereas the tangential one is you'll have to use like sum of forces equals mass times acceleration there. Yep. We'll see how that comes into play in question 2, I think. And lastly, we have polar coordinates. So polar coordinates are probably the least intuitive because we're not operating necessarily on like a grid like this. So, you know, before we were talking about x, y, and something like this for tangential and normal, right? Which would just be like a rotated xy plane pretty much, right? Instead, for polar coordinates, say we have the path of a rocket that goes like this, and we have a satellite observing it. You'll see this in action for question 4. Let's say you have a satellite observing it, yeah? So basically, the radius from the satellite to where the rocket currently is can be described with r, which is radius, right? And then we will also have the rotation, which will be described as theta, right? So, how do I explain this? So you'll be using stuff like r dot, theta, theta dot. So each of these dots means that you differentiate it, right? So it's the change of the previous one. So here's the radius and here's the angle. Angle might be there. So this angle will be changing over time, and so will the radius. So if this is the path, the radius might be increasing over time as it goes further away from the satellite, and the angle theta will also be changing with respect to time, which is our radial velocity and angular velocity. Yeah, angular velocity. And then there's also radial acceleration and angular acceleration as well. But the good news is that how it kind of works for our grid system is our grid system looks like this, where these are the positive directions. And it just kind of makes sense when you see it in practice, right? It might not immediately look like it makes sense because as it changes over time, the direction of the grid's system will change as well. So if it was like, like here or whatever, but the maths works out without too much problems. A particular case of polar coordinates, a special case for polar coordinates undergoing a curvilinear path is if it's a circular path, right? So these two words don't mean the same thing. With a circular path, it's like literally a circle. And for a circular path, the radius is fixed, so the radius is constant. Yeah, and you'll see later in the formulas when it has a constant radius, that means that the change in radius is 0 and the acceleration, radial acceleration is 0 as well. And it will modify our formulas slightly for that, right? For sinusoidal motion, it's basically you use the same formulas as you do for the curvilinear polar motion, but it's kind of just a different application slightly. So the curvilinear polar motion might be useful for a rocket being tracked by a satellite, for example. but sinusoidal motion might be useful for like a robotic arm. I'm going to draw this really badly. But if you can imagine this is the path that a robotic arm that's swinging around is taking, you can pretend like this robotic arm is like extending and contracting and rotating, but like those two things are happening independently of each other, giving this kind of pattern. I can hear the rain. Maybe it dies down later. Right? So yeah, that's kind of how it works. Zoom out for a second. Anyone want to copy any of that? Is that too hard to see? Is that okay? I'll leave that there if anyone's still copying. I'm going to check the chat on my phone. Okay, I can't get it to work. Okay, no one's said anything in chat, all good. Does anyone have any questions in person here? Oops. Oh, whatever. Okay, cool. So we will move on to the next part. So what I've decided to do is break up these formulas, which you'll need to do the questions, into 6 sections. So I've grouped these two together. Because essentially you're using the same formulas for the grounded motion, right? Projectile motion, 1, 2. Relative motion, I'll put that on 3. Curvilinear, 4. But you use different formulas for the curvilinear motion when you're using the NT system and the polar system, right? But you use the same ones for curvilinear and sinusoidal for polar. Circular motions, the formula is slightly different as well. So yeah, I'm gonna scroll down and you'll see what I mean. So for grounded motion, right, so that might be like, again, a box being pulled by a string. You want to be using F as ma, and sum of the forces is equal to 0 for the grounded, or like the normal direction pretty much, right? The weight force is always going to be pointing downwards. If we're looking at the free body diagram from elevation view, right? So that's up, down on the y-axis. It's always going to be downwards, even if it's on an incline. Yeah. If you want an example of how this friction works, refer to workshop 1. I believe the last question on workshop 1. But yeah. Yeah, you pretty much always go from weight force to solve for normal force to the friction ones, right? When you're solving for those box questions, pretty much. For projectile motion, right, so we're looking over here. Yeah, everyone does this slightly differently. The way that I did this back in high school physics is we got given like 4 or 5 kinematic equations, and then you just pick the best one for the situation. But now I found the best way to do it, and especially with the questions which you're kind of provided, a lot of them will want you to kind of have these like algebraic, I don't know, so yeah, you kind of just want to derive the equation of motion yourself, which sounds hard, but it's honestly pretty much the same thing every time. But yeah, the first thing that I do is I split up the initial velocity into two components. So what I mean is, like, if someone's throwing a ball and that's your initial velocity in that direction, then Vxo is that way, Vyo, I'm just splitting it like we've been doing since the first workshop. And this is assuming that the angle that you're given is that butterfly angle. So we're using theta, right, to denote that. Then we can use cosine and sine. The next thing I do is remember our model for projectile motion, and that's that horizontal acceleration is 0, right? No air resistance. And the vertical acceleration is 9.81 meters per second squared acting downwards, so towards the Earth, right? And here's the functions which I kind of go off of, and they're pretty much the same every time. What I like to remember is the function, right, is equal to the initial plus the change, right? And so here's how you can think of it. So the function for the horizontal velocity is equal to the initial horizontal velocity plus the change, which is the acceleration multiplied by time, right? But for the horizontal one, we know that that's 0, right? So you can completely take out that component for horizontal. And for vertical, it's kind of this way, right? This is assuming we're using this system, right? And when you integrate it, you can get the expression for displacement. So the x-axis displacement is simply equal to this multiplied by time, the initial horizontal velocity. And remember, since this component was 0, we don't have to do anything with that. That just, yep, this is 0, right? Yep, and then for the vertical direction, we're doing a similar thing, except we have to consider that our acceleration was equal to something. And so we raise the power and then divide it by 2, and you end up with this expression. So yeah, in every question I just derive it now. Yeah, I don't know, it just helps me to consolidate that idea myself. Yeah. Does anyone have any questions so far? I'm going to check the chat. Looking good. All right. So, okay, relative motion. This concept is kind of new. And for every relative motion question, I like to break everything up into the I and j unit vectors first. But I didn't write this in the equations because here I want to demonstrate what I'm talking about for relative motion. So here's where you should kind of recall the theory behind what vectors are and how vectors work, vector addition, whatever. Because you're pretty much just drawing like tip to tail arrows for the vectors, right? So you'll see that here's the way I always remember it when I'm writing out, because sometimes you're not gonna have it as called A and B, right? So later you'll see in rigid body kinematics, and when you have like relative motion questions for that, you'll see that sometimes these are called point C, point D, point O, whatever. So it's not always going to be this formulas, right? It's just A and B. What I like to think of it as is you write like A, for example, and then you write B, so your first point and your second point. And for the thing that you add on to it, do the first one, like the one that was on the left, slash the one on the right. And so what does that slash thing mean? It means what is the velocity of A relative to B, right? So from the perspective of B, what is A? So when you think about this too hard, like it's gonna do your head in, right? So the best thing to do is, in my opinion, just draw out like the tip to tail, and it makes more sense. So what I like to do is I like to draw the A and B ones originating from the same point, right? So over here. And then like looking at the formula, it's saying that the final location, when you add vector B to the vector of A relative to B, it should end up at the same point as point A, right? So the left-hand side and the right-hand side should start at the same point and end at the same point over here, right? Yeah, I don't know, that's my way of remembering it myself. Similarly but different, I'm gonna start highlighting. So B was here, but now B is over here instead, right? Oh, I did the wrong color. So yeah, notice I didn't write the same thing for AB and VBA. So again, I'm thinking about like, you write the one on the left and then the one on the right for this formula, right? And when you draw the arrows, it should end up such that the left-hand side and the right-hand side start at the same point and end at the same point over here, right? Yeah, I don't know. It helps for me to remember like that. But if that was, yeah, if you have your own way of remembering that's better, then yeah, just use that. Okay. Cool. So now we'll go on to curvilinear motion. So curvilinear motion, for when you're using the normal and tangential coordinates, we have these formulas for acceleration. These two are probably the more common ones that you'll be using. I think you might use one of these in the questions that are provided in the extra practice, but for the most part, the acceleration ones are the key ones here. So actually, even this one is not really much of a formula to remember. So the main one you have to remember is that the normal has this almost like, it has like this geometric kind of formula almost, because it's based on the curvature of your path. So that's your path. It's based on this radius here, right? And if we have like something traveling on this path, we're pointing the normal component inwards towards it, centripetal acceleration, right? But for the tangential component, it's the derivative of v, but I don't know, I guess for the questions, it's more just like to do with this. Sum of the forces in the tangential direction equals mass times that, and usually you're solving for whatever forces that you come across in these questions, right? Kind of like that way, right? So basically, yeah. Okay, I'm just talking too much now. So yeah, hopefully that kind of makes sense. Yeah, sometimes you'll have to use the arc length, so that's the arc length. And sometimes you'll have to use the angular velocity. It's kind of two different notations. So that one is omega, lowercase omega, the Greek letter, right? But it can be seen as that as well. That's also angular velocity, right? Yeah. Cool. But yeah, I like to only stick to this notation for the polar coordinates. So for the polar coordinates, we have our radial velocity. We have our radial velocity and our yeah, okay, you know what? It'll make more sense like when we do the question. But yeah, there's like formulas for them. And when we look at the formulas relative to a circular path and when r is constant, what ends up happening is that the change in radius is 0 and the change in radius is 0. And so all of these components with r dot or r dot dot get cancelled out. Right, so you're just left with these bits. Right. Yeah. So those are the formulas. All good. Cool. Online. Will be. No. So to answer your question, Leonardo, I just drew it like this, but it's not always the case. So if you instead have vectors which look like this, VA, VB, right? Then this one, it's not going to be necessarily perpendicular, right? And you will see in rigid body kinematics, you'll have to use like the sine laws or whatever, cosine laws, that kind of stuff. Mainly the sine law, but yeah. So these triangles aren't always nice, basically. Yeah, cool. All right, so what we'll do is we'll do question 1, and then I'll give you a break. And we'll continue and do 2, 3, 4. So for the first question, is a projectile motion question, right? So it's a boy throws this ball, and it hits the top of the roof at point C, right? And it's standing d distance away from the house, which is, and the house is like 8 meters long or whatever. So like to get to the roof of the house is right in the middle, right? Yeah. All right, so we're given that VA is 15 meters per second, right? So that is that. And we're not given the angle that he throws it at, and we're also not given the distance away from the house, right? So we can solve for these separately. So yeah, keeping in mind that we're splitting up our coordinates into x and y, right? Do these two numbers, right, the angle and d, you gotta think about, do these numbers like depend on each other? And the answer is you can actually analyze the vertical and horizontal components separately and then find, find them separately. So, okay, you know what, I'll just dive into the question, makes more sense. Okay, so the first thing I like to do is split up VA. Also, I called it like VAO or something before. Anyway, so the x component of that is going to be that. The y component is this. Right? Well, we don't know the angle. That's what we're going to be solving for. but this is just like a little preliminary step I like to do. We do know the initial acceleration, initial velocity, right? Okay, and then the next thing I like to do is note down this. So and now we're ready to derive functions for both of these, right? So I'm going to start with the y direction. And the reason I want to find y first is because I can find the angle. Sorry, I'm not explaining this very well, my bad. I basically want to use the y direction, or the vertical direction, to find the angle, right? Because I know everything about that direction except for the angle. And then once I solve for that, I can solve for d, because in the horizontal direction, my unknowns are the distance d and the angle. So we're going to analyze the vertical direction first. And the reason why we know enough about the vertical direction, first I'll derive my function. And this would be the vertical direction. So I'm just subbing in all of the things that I already know, right? Okay, and then we know one additional thing about the vertical direction, and that's that once it hits the tip of the house, the ball reaches apex, right? And what we know about the apex of an arc is that the velocity in the y direction is equal to 0, right? So it can't go any further up. And so the speed is, it's not increasing anymore. So at point C, the ball reaches apex. Right. So the V right there is equal to this. Right. And so now we just solve for the angle. Find that the angle is equal to oh wait, am I doing this wrong? Wait, sorry, getting an error on my phone. Okay, sorry, this is a bit sloppy, but I can't get my phone's like notes and stuff to work. So I'll let you take a break now. I'll fix this up and then we'll continue right after the break, right? Sorry about that. Sorry, will explain question 1 after the break. Is the QR code? So if you could just take your attendance. still working out. Does anyone have any questions? Okay. So I'll explain it properly after the break.
I know this is a common question. We tried to stop the screen.
Sure.
Like the projector is kind of
Oh, wait, does this QR code not work? So,
yeah, just like right now.
I'm here now.
The projector kind of flickers right now.
Oh,
Just trying to.
well, let me turn it off and on again, but I don't know how much I can do to fix that. Yeah, I'm not sure how to fix it. I think it's just a problem with the room, man. I'm gonna check if anyone has questions. Oops. Oh, does anyone still need the QR code? Has everyone got the QR code? Be back in like 2 minutes. Oh. Let me bring that up. Yep. All right, I'm gonna get started again. All right. Okay, I'm sorry. This question I'm not explaining very well. Let's run it back. All right. So basically, you got this guy. He's throwing a ball at the top of the house, right? And we don't know how far he's standing away from the edge of the house, but we do know that when it hits the top of the roof, it reaches the apex of the throw. And we also know, which I forgot to mention before, that we know the vertical displacement that the ball travels as well, right? Okay. So that's the information that we're given. So we've decided to analyze the vertical direction first because we have more information pretty much. So what I've done so far is, one, I've split up the velocity into its components, the velocity that we were given. but we don't know the angle, so that's still unknown, right? So I've derived the functions for, I've derived one function, which is the function for velocity in the y direction, and that's what we have here. So what I'm going to do is I'm going to call the TC, and that's the time it takes to travel to point C, right? So I realize now, and what I forgot as I was not able to access my notes earlier, is that we have two unknowns, okay, using this equation. So what I'm going to do is I'm going to rearrange it for TC, and this is going to involve simultaneous equations because we're not given as much information as we would for a simpler question. So TC is equal to this. Right? Which we will call equation 1, right? Okay, so next, what I was saying earlier about the house, like the height of the house and the height of the person, is that we know the vertical displacement which the ball has to travel upwards, right? Because we were given that the house was at 8 meters above the ground, and we're given that the person was 1 meter above the ground or whatever, right? So we're going to derive a function for vertical displacement. So all we're going to do, right, is have a look at this, and we're going to integrate it. I'm going to integrate it, right? Oops. So that is this one integrated with respect to t, brings it up to t to the power 1, right? And, oops, kind of doubled up. Yeah, so that's what we've done. Okay. And so I'm going to write this out with our substitutions in for these things. Sy is this. Right? And we also know that Sy is 8 minus 1, right? Because the height of the house is 8, and then the dude was 1, right? And the projectile goes like that. Seven is equal to all this stuff, right? But what we're going to do is we're going to replace t with Tc, right, which was equation 1, right? So what this is actually going to look like. It's like this. Which looks horrible, but that's all good. Because when we expand it out, you can do it bit by bit. What I like to do is the constants, right? You just chuck this on your calculator, you get this. Well, I've just multiplied 15 by 15, right? And then the signs are multiplied together. And similarly here, oops, here are the constants, right? So that one, well, actually what happens is we can't forget about the squared. So when you're doing this in your calculator, you will end up with this. Right? And the sine is squared. So it just ends up looking like that. It's not too bad. So when we're solving for this now, on my calculator, I grouped these two components together and factored it, right? And what I've done in one step is, on my calculator, this divided by whatever that factor was, whatever these two were, right? That's given me this. Right? And then what you can do is you can square root it, both sides. And then take the inverse sign. And you get this. Right? And now that's our angle. We've finally gotten there. Okay. So once we have our angle, right? Back at our question. We have that that's 51.38. Now we're looking for D, right? And so we're going to have to analyze the horizontal direction. But the good thing about the horizontal direction is that it doesn't have any like acceleration, so it'll be a little bit easier. Okay, so firstly, remember what we derived earlier for time? The time it takes to get to C, right? We've kind of got an expression for that now because we know that that's 51 point, was it? 38, right? So TC is now what we had before. Replace that. And when we get that on our calculator, it's equal to this, right? So now we have the time it takes for the ball to be thrown and then get to point C. Now we're looking at the horizontal motion. And yeah, so we know that this is the case. And we know that Vx is going to be constant, right? Because there's no horizontal acceleration. So what we worked out earlier was this, right? When we were splitting up the components, velocity, this is the horizontal part. And since we have this now, look like this, right? That's not too bad. We integrate it to get this, right? Vx multiplied by t, right? Oops. So all we've done is gone from this up, this here, and then integrate it with respect to time, and then we end up with this t. And so this part was 15 because 51.38. Oh, sorry, we can just replace that. And so for t, we're going to replace that with tc, which we worked out earlier, right? The time it takes for the ball to get to C, which was 0.195, right? So that's equal to 11.19 meters. But remember, D is not the same as Sx, because Sx is here, right? Sx is the time it takes to get from A to C. So we're going to have to subtract off 4 meters. And that gives us our answer. Yeah? Okay. We got there in the end. Anyone got any questions? I'm gonna check online. Okay, looking good. All right, that was question 1. Here we go. So, question 2. Here's an example of when we have to use our normal and tangential acceleration for the normal and tangential coordinates. So we have 2 sliders with this mass, right? So that's MA, MB is 0.2, right? And we have this force that's pulling slider A due north, I guess you can call it. Yeah, and then there's this rope, right, that's kind of keeping them tied together, right? So there's going to be some sort of tension force in this question. And it says that, what does it say? The system starts from rest, right? And that's, yeah, we're going to analyze it in this particular situation, right? So these angles, and it's starting from rest. Okay, so, oh yeah, actually, so, because the system starts at rest, right? So at t equals 0, v equals 0, right? Because it's starting from rest. And so this is going to affect one of our formulas, which is our normal acceleration, right? And because of this, the normal acceleration is going to equal 0 meters per second squared. But the tangential for A and the tangential for B, right? These two are going to be intertwined because of this rope, right? So we're just going to call it AT. That's kind of the other trick of this question, right? Yeah, they're going to have the same acceleration pretty much because of how this system's set up, right? So from a plan view, I've just redrawn it. I'm going to draw a free body diagram at what's happening at A, right? So we're going to use Newton's third law, analyze that part. So we have this force pulling it 4 newtons in the y direction there. Yeah, okay. And then basically, let's look at this question again, right? So these are sliders in a, these are sliders in a slot, right? And so the surface is going to give a normal reaction here, right? And specifically, it's going to look like this on a diagram. It's going to, yeah, push off the surface, which causes, yeah, anyway, yeah, there's going to be a normal reaction pretty much, right? And the other thing that's happening in terms of forces is the tension force here, which is at 45 degrees, right? Just because of, I don't know, just because of looking at it, right? So that's our free body diagram at A. I'm also going to draw the free body diagram at B before I do the calcs on A. So it looks kind of similar, but there's not going to be a point force pulling it, right? But there will be the tension force and the normal force, right? But the normal force for B is going to be acting kind of in that up direction, right? Okay, so that's our situation. So what I'm going to do is we're going to take the sum of the normal forces and tangential forces, but I take the positive direction as the direction of acceleration, okay, or the direction of motion. So what I mean is the tangential is going to look like that, right? And well, this looks normal because we've been taking, with static equilibrium, we've been taking the sum of forces in the up direction and the right direction. But you'll find that when we're taking the sum of the forces in the normal direction for this particular case, you're actually going to want to point the positive direction towards the direction of acceleration, which is centripetal acceleration, right? So in towards a circle, right? So for the tangential direction, it's going to look like this, right? It's the mass of A, because we're just analyzing the free body diagram at A, and its tangential acceleration, which we've established is going to be, it's going to be the same for the body A and body B. The next thing we're going to do is we're going to list out the forces in the up direction, or the vertical direction. We're in plan view. Maybe I'll just call this north to avoid confusion. Right? So in the north direction, we'll do 4 minus t. Using this convention, we'll say cosine 45, right? And that works out to be, what I'm going to do is, because I know what's coming up, which is a bunch of simultaneous equations, I'm going to keep the constants on one side and the other variables on the other side. So it'll look like this. Yeah, so here's the constant, and our variables t and at. A, like tangential acceleration, it's going to be set up like that. Okay. So next, for our normal acceleration, we've established that the normal acceleration is 0, right? So this is actually in static equilibrium, right? In the normal direction. It's equal to NA plus t sine 45, right? And so yeah, like before, we have two unknowns, but we're going to set it up so that the constants are on the same side. So I'll write it like this. Is our second equation? Okay. Next, we're going to go over to a free body diagram at B. And yeah, sum of the normal forces is equal to mass at B, normal acceleration, which was 0, is equal to NB plus t sine 45, right? And yeah, similarly, NB plus t sine 45 is equal to 0. And then lastly, the motion's going to the right in terms of the tangential motion, right? So we're going to take some in that direction. That's 0.2 we're given in the question. And then Yeah, the only force in this free body diagram at B acting to the right is T cosine 45, right? So we know that AT minus T cosine 45 divided by 0.2 is equal to 0. Right, so now we have four equations which we're going to set up simultaneously, and you might be able to notice which method I'm going to use because of how I set this up. But yeah, I'm going to use a matrix. So this is a 4-row by 5-column matrix, and so how I do this is basically each row is equivalent to one of our equations, right? And we're going to have the constant, which is in front of each variable listed in each of the grids, right? So for t, on equation 1, the constant is this, right? The cos 45 over 0.2, right? And for a, you can't see it here, but there's an invisible 1, right? So that one is 1. Go back to the equation, right? We don't have any 0 NA and 0 NB, so those will both be 0 in our grid. But on the right hand side, constant is 20, so there's going to be 0, 0, and 20. Okay, that's how we're going to set it up. So you can also do this using substitution, whatever simultaneous equation methods you like, but I find that when I have SimulLab next to me, this is the easiest way, right? And so for equation 2, similarly for t, it's sine 45, for NA it's 1, and for the other variables is 0. And for equation 3, it was very similar, except that NB was 1 instead, right? So equation 4, t was negative, right? Negative 45, negative cos 45 over 0.2 for t. For a, it was 1. And for the rest, it was 0, right? Okay, so we've got everything set up. When you put this through SimulLab, what it does is it row reduces everything, and so everything wants to become 1 here. And then all these will be 0. And whatever these numbers end up being on the right is going to be equivalent to, the first one will be equivalent to t. So it goes like that, then across, that will be t. This one will be AT. This one will be NA. This one will be NB, right? That's how it'll work. Sorry, I'll undo everything. That's not going to let me undo everything, eh? Oh man, trying to rub this out. Oh, actually, one thing I noticed as I was putting it through SimulLab. Yeah, I noticed that the matrix calculator doesn't really like cos 45. So you want to put it in surd form, right, rather than the cosine form. So actually, that's what I've done here. I've just replaced the cosine and 45 and sine 45 with the surd form, right? Yeah. And then it works. Yeah, then we get these. That gives us the answer for everything. Yeah. Does anyone have questions? Nope. Come on. Where do I find these notes? The full ones, not any of the questions. So Google Drive / Moodle. Right. Google Drive for the drafts. Google Drive plus Moodle for the final copies, which I'll upload tonight. Yep, so yeah, basically if you don't have access to the Google Drive, if you added your name, your email address into the attendance form, then I send it through after every lesson. So you'll have a link to the Google Drive. Otherwise, I also send it into the workshop chats after each workshop's done as well. Yeah. Okay, we're gonna keep moving on. So, this question says, car A travels east with a constant speed of 36 kilometers per hour. Car B, this one starts from rest and then accelerates south at 1.2 meters per second. And then it's asking about the relative velocity and acceleration of car B with respect to A. So again, I'm going to write that out as VB with respect to A and AB with respect to A. That's what it's asking for, pretty much, right? And it'll be 5 seconds after it starts accelerating, right? Okay, so I've redrawn the question, but I've used the I and J unit vector notation. I just find that it's a little bit easier. So, but the first thing I'm going to do is I'm going to convert VA, which is currently in kilometers per hour, into meters per second. So it looks like this. Here's how the conversion works. So 1 meter a second. There's 1 meter a second for every 3.6 kilometers per hour. And you can remember the right way around for doing this. So whether you want to multiply by 3.6 or divide by 3.6 based on logic. So if you're driving a car and you're going, for example, 40 kilometers per hour, right? If I times that by 3.6 to get meters per second, you're going to be going like over 100 meters per second, which doesn't make any sense, right? So you're definitely going to be dividing by 3.6 in that case, right? Which is what we're doing, but for 36 kilometers per hour. And yeah, with this maths, this is how the units cancel out as well, right? So you're left with just meters per second. And that's all happening in the I direction. So VA is 10I meters per second, right? And yeah, just based on how the question is worded, it's going at a constant speed, right? Constant speed. So there's no acceleration happening here, right? Yeah, so now we've kind of got everything we need for A. Now we just have to do it for B. And B is going to be a little bit different because it starts at rest, right? It starts from rest and then accelerates, okay? So this is why it's useful to derive all the equations yourself, equations of motion, because you have a better understanding of how everything will be working. So VB, right, it's going to be the initial velocity plus the acceleration multiplied by time. Again, I'm going to reiterate my rule of thumb. So this is the function. It's equal to the initial plus the change, right? Change over time, right? And so this one's from rest. So that component's going to be 0, right? And so VB is just going to be equal to our acceleration, which was negative 1.2 j, right? Right like this. Yeah. So this is the unit vector for direction, right? And it's in that negative direction. And then here's our acceleration multiplied by our unknown t, or like our, well, we're going to plug into the function, basically. And then these are the units. So there's a lot of things going on there, but yeah, that's what it means. So now we found that. And we found the velocity for A, which is going to be constant. So next we're going to find velocity of B relative to A and the acceleration of B relative to A at time equals 5 seconds, which is in the question. So from what we wrote just a second ago, we sub in 5 seconds, right? We get that this is negative 6 j meters per second, right? And when we sub this into our relative velocity formula, right? Let's just draw it out actually. This might help. So VB, right? VB was this one, and it was negative 6j, right? Makes sense. We draw VA from the same point. And that one is 10i, right? So 10 going to the right. And now, yeah, I think of it like this. So the left-hand side and the right-hand side have to start and end at the same point. So the right-hand side, this one has to go over here. And then, yeah, so we can just split it into component vectors. How good. Works out very nicely there. So that's our relative velocity in terms of component vectors. Yeah, that's when we rearrange for VBA basically. Yep. Okay, and now the last bit is asking for, so that was VBA. Last bit's asking for the acceleration as well. So basically looks like this. Is our function, oh sorry, is our relative velocity. And we worked out, we were given that the acceleration of car B was 1.2 south, right? And we were given that car A doesn't accelerate, right? So in other words, it's this. Right. And so when we rearrange for A relative to B, it's simply equal to AB, which is this. And if we want to draw out a little arrow diagram thing, basically this. It's kind of a bad color. Change the orange. Cool. Any questions? No? All good? Check online. Cool. All right. Okay. We've just got one more question. So here's our satellite tracking our rocket, and here's where we're going to use our polar coordinate system. Worst part about this question is that everything's in feet per second, or whatever. Look at that. Okay. So let's read this slowly. So it's asking when the angle is 30 degrees, right? This is like one instant in time. We know that the radius is measured to be this, right? That in feet. And the radial velocity is 400 feet per second. And the angular velocity is 0.8 degrees per second, right? And the acceleration of the rocket is only due to gravity, right? And at that particular altitude, right? Okay. So here we're like really far, really far off the ground, and so you can't instantly assume that gravity is 9.81 meters per second acting downwards, right? So they just give it to you, but it's not going to be 9.81 when you translate it. Yeah, it's given as this. Yeah, and then the question wants us to determine the velocity v of the rocket and the radial acceleration and angular acceleration as well. Okay, so the first thing we're going to do is we're going to get rid of these horrible units. So, we'll write out our angle first. So the angle is 30 degrees. But I'm also going to list it in terms of radians because it'll be useful for when we plug in to our formulas, which are listed on the page above, right? So we want to convert this to radians. Right? We get that is this. This was listed as 0.8 degrees per second for the angular velocity, right? And exact same thing, we can just multiply it by, I'm just going to copy this over. It's the same conversion because we're just converting the degrees, which is on the numerator, over, right? So that is that. Right? And lastly, our angular acceleration is unknown, so that's what we're going to be solving for. Okay. Next, our radius was given as 25 times 10 to the 4 feet, so we're going to convert that. This is something I had to look up online because I didn't know what the conversion was, but 0.3048 meters per 1 feet, right? Yeah, I don't know. Yeah, okay. And then, so we're just going to get rid of these units, right? And we're going to end up with meters. All good? Right. And we're also given the radial velocity, which is 4,000 feet per second. Same thing, because the feet is in like on the numerator, we can just do the same conversion. gives us this. Right? And our radial acceleration is unknown, so that's what we're going to be solving for later. One more thing I want to mention is g, right? So g, the acceleration due to gravity, I was saying, is not equal to 9.81 in this particular question. So you want to take what they gave, right, which is in feet per second squared, and convert that. Which gives 9.57 meters per second squared. So that, again, that's slightly different, right? It's slightly lower. It makes sense because you're further away from the Earth, so the gravitational pull won't be as strong, right? Okay. So basically, VR. So here's where I cut myself off earlier because I prefer to have the definitions in front of me as I'm explaining it. So VR is basically the speed the rocket is moving relative to the origin, right? The origin being the satellite, right? So yeah, and then v theta is the speed the rocket is rotating. Okay, so that helped me kind of understand it a bit better. So if we're looking at it, right, you can think of it like this. So imagine this is the arc, right? This is path, and yeah, we take the directions like this. You know what? And these will be the positive directions, right, that I've indicated. And this was 30 degrees because we're looking at the rocket at this particular instance, right? Yeah. Anyway, so there's a formula for VR, which was R dot, right? And we know R dot because we calculated it earlier, right? So this isn't that at all. That was that. The next one is the speed the rocket rotates, which is the radius multiplied by the angular velocity, right? And we've calculated both of these as well. That was this one here. And our theta dot was this one here. So yeah, this is in radians. Oh, sorry. All right. Yeah, I kind of had to think about this a bit myself, but basically, so this was in radians per second, right? And this was in meters, and it ends up as meters per second. And the way I like to think of it is that radians are kind of like just numbers. They're not really its own unit, right? Kind of like unitless, right? I don't know. That helped me kind of just accept that. Yeah. That's it.
That's supposed to be 7.62 times 10 to the first.
Oh, did I write it wrong? Yes. Wait, sorry, which bit was wrong?
Here's
Yeah.
yeah, like 10 to the power 4 by 0.3, so if you could small number.
Wait, am I looking here or?
Yeah.
Oh, wait. So I'm multiplying 25.
25, sorry.
Yeah, it's 0.3, I think. Yeah.
No, sorry.
Oh no, it's all good. No. All good. I thought I wrote like something here wrong. No, all good. Yep. I'm gonna check online for any questions as well. Looking good. Okay, and now, yeah, like any other, so we had if the radius or whatever between the satellite origin here and the rocket here was r, and then we had our directions going like this way and this way, right? This was for r and this was for theta direction, right? Our VR acts in the r direction, and our v theta acts in the theta direction. And same for, yeah, I'll just draw it here. Right? And then same for AR and A theta. So I guess the useful thing about polar coordinates is that the R, the velocity and the acceleration. Oh no, it's not the R. Yeah, like the displacement, the velocity and the acceleration are all going with the same grid system. And that's different to our normal and tangential ones for centripetal, what's it called? Curvilinear paths for NT, because sorry, the lectures do a way better job of explaining this, but if this was our displacement, right? Our velocity is tangential, right, to the path, and our acceleration is normal. Oh, sorry, our normal acceleration is like that way. I didn't select a very good point for this. Select it over here. Sorry, I'm kind of illustrating I'm trying to illustrate a point that I haven't fully prepared, so this isn't the best explanation. The velocity on a curvilinear path follows, is tangential to the path, right? And then for the acceleration, it just points towards the middle of the circle for the normal component, and the tangential component is tangential, right? Should be going somewhere that way. And so the net acceleration is actually that one, right? Yeah, and anyway, my point is, similar things going on, so we use Pythagoras, right, to get to the velocity for this. Sorry, that was a bit of a tangent. Okay. Get this number. Right, and that's after subbing in our values here. Right? Yep. Okay. Actually I have prepared it. I just didn't scroll down. Okay, I'm going to delete that because this is a poor example. Okay. So basically we're given in the question that the acceleration is only due to gravity, so acting only directly downwards, right? And it was given as this. Okay, I'm going to redraw that situation again. That's at 30 degrees, that's the origin, that's the rocket. Here are our positive directions. Right? Okay. Here's our theta component of acceleration, and here's our radial component of acceleration. right? And we know this because our net is just going to be gravity, right, which is pointing directly downwards. So it looks like that, okay? So essentially, AR is gravity, cosine 30. That's 30 degrees here, right? Cosine because it's that one, right? And our positive R direction was acting away, right, from our satellite. So yeah, basically that's negative. And then A theta is positive. It's going in the positive theta direction. And that one will be sine 30. That is a 4. Okay, cool. So now, basically, because we were given gravity, which was the magnitude, what do you call it? Okay, pretend on an XY plane, right? Yeah, we have like some resultant force, and then the X component of it and the Y component of it. We were basically given the diagonal equivalent, and then we split it up into its components. So that's just what we did, but in the context of this instead, right? So AR is a rocket radial acceleration relative to the origin, and then A theta is a rocket rotational acceleration. Yeah, and so since we actually worked out these, we've worked out the left-hand side essentially. I'm just going to plug this in, right? And this is going to be equal to our formula, which I listed above. Right? And the unknown that we're actually going to be solving for is r dot dot, because we know these numbers, we just have to plug it in. The numbers were these. Right? So now, when we're solving, we just solve for r dot dot. Right? Get that r dot dot. 6.562 meters per second squared, right? And if you want to double check the answers, it's the same as feet per second squared, right? But I prefer this one, right? So for the, I'll scroll up a bit. So for rocket rotational acceleration, similar deal. We're going to plug in what we worked out a second ago for the left-hand side. Here's the formula. If you want the derivations for these formulas, I believe the lecturer has done it in the lectures this morning. And then what we're working out, right, is this one, because the rest is known. So that is yep. And when we solve for our unknown here, right, equal to this as the left-hand side. Yeah, get this answer. Okay. Yep. Anyone got any questions? Yeah, so one more thing. I've included extra practice questions on Moodle as usual and on the Google Drive. I've also decided to include one of those questions which uses this grounded motion and has like friction. And that's just building on like a question that you saw in workshop 1, the one with the friction involved. So, I don't know, I guess like in the mining school, they consider that kinetics, I think. And in the civil school, they consider that kinematics. So I actually don't know whether that's kinematics or kinetics, to be honest. And like the mech school, like I think that's kinematics. It's like I don't even know. So like I've just included it so you can do it earlier and before Friday if you want to try that question. Yeah. In general, like kinematics is the motion of particles, and like you don't really analyze the forces. Actually, now that I think about it, we analyze the forces not for projectile motion but for curvilinear motion. So maybe it is kinetics. Kinematics. Maybe it's kinematics. Yeah. Okay. Sure. All right. Yeah. If no one else has any more questions, you're free to go. Otherwise, if you want to ask questions, come up front, online, check for questions. Yeah, but otherwise you're free to leave for people tuning in online. That's the QR code. All good. Thank you.